Three astronomers studying Comet 3I Atlas are confronting three observations that defy standard explanations. Harvard scientist Avi Loeb published calculations showing the comet's anti-tail, a structure pointing toward the Sun, might actually be thousands of fragments travelling together as a swarm. At the same time, new data revealed the object pulses in brightness every 16 hours, with an intensity pattern that appears inconsistent with normal rotation. And the ALMA radio telescope detected a chemical split no one expected. Methanol concentrated on the sun-facing side, and hydrogen cyanide on the opposite hemisphere. Each of these findings stands on its own as unusual. Together they form a puzzle that has no clear solution using conventional comet models. The anti-tail has persisted for months. Anti-tails are not completely new. Comet Arend-Roland in 1957 and Comet Hale-Bopp in 1997 both displayed them. In those cases, scientists determined the structures were optical illusions. When observers watched from different angles or at different phases of the orbit, the geometry shifted and revealed the tails were actually pointing away from the Sun as expected. The tails appeared to point sunward only because of the specific viewing geometry from Earth at that moment in time. Once the comet moved along its orbit or Earth shifted its position, the illusion broke down and the tail revealed its true orientation. But 3I Atlas has been observed across different viewing geometries and different orbital phases for months, and the structure remains stable. Astronomers have tracked it from multiple observatories at different times with different instruments, and the anti-tail persists. That persistent stability across so many independent observations is much harder to explain using the optical illusion model. It suggests that whatever is creating this structure is a real physical phenomenon, not just a trick of perspective. One hypothesis involves unusually large dust particles. Normal comet dust consists of particles smaller than grains of sand. Solar wind pushes these tiny particles away from the Sun easily. The pressure from sunlight and the charged particles streaming out from the Sun overpower the gravitational pull, and the dust gets swept into the familiar tail pointing away from the Sun. But if the dust particles are much larger and heavier, they move more slowly. Large, slow-moving dust particles can create unusual tail shapes that, depending on exactly where Earth is positioned, can appear to point sunward even though they are actually being pushed away. It is a matter of angle and timing. The particles are still moving away from the Sun, but because they are moving so slowly and because we are viewing them from a particular angle, they can appear to form a structure pointing toward the Sun. This phenomenon has been observed in a few other comets before, so it is a known natural process. Most astronomers think this is probably what we are, seeing with 3I Atlas. But Avi Loeb argues that for this explanation to work, the object must be significantly larger than observations suggest. Current observations place its diameter at around 3 miles. Loeb contends that producing the observed anti-tail structure through large dust particles alone would require the nucleus to be much bigger, with more mass available to produce the necessary volume of large dust grains. If the nucleus is only 3 miles across, then the mass budget does not support the large dust hypothesis as easily as it would for a bigger object. This is where Loeb's alternative explanation comes into play. Loeb has proposed a different mathematical explanation based on precise orbital mechanics. 3I Atlas is showing non-gravitational acceleration. The object is not following a pure gravitational path. Something is giving it a small extra push. This push usually comes from particles jetting off the surface. When gas shoots out in one direction, it creates a tiny rocket effect that nudges the object in the opposite direction. This behavior is normal for active comets. We see it all the time in our own solar system. Comets like Halley and Encke both show non-gravitational acceleration from outgassing. So the fact that 3I Atlas shows this behavior is not surprising in itself. Loeb's hypothesis suggests 3I Atlas might be surrounded by a cloud of smaller fragments or debris. These fragments would be travelling through space alongside the comet at roughly the same speed. They would have been released from the main nucleus at some point, either through gentle sublimation or through some kind of disruption event, and now they are travelling as a loose swarm. But if these fragments are not producing jets themselves, they would be following pure gravity with no extra push, just the Sun pulling on them. Over time, 3I Atlas gets nudged slightly away from the Sun by its jets while the fragments are not. They simply follow gravity, which pulls them toward the Sun. Even though this difference is tiny, over the vast distances involved in space travel it adds up. The main nucleus moves on a slightly different trajectory than the fragment cloud, and the separation between them grows. Loeb calculated exactly how much separation this would create. At 3I Atlas's current distance from the Sun, about 160 million miles, the offset between the main object and a cloud of fragments would be about 33,500 miles. When viewed from Earth, this separation would appear as about 0.7 arc-minutes of angular separation. That is a very specific prediction. It is not a vague estimate. It is a number derived from the known non-gravitational acceleration, the distance from the Sun, and the geometry of the observation. And the November images do show a sunward glow measuring close to 0.7 arc-minutes. The math matches the observation. That does not prove the swarm hypothesis is correct, but it does mean the hypothesis makes a testable prediction that appears consistent with what we are actually seeing. Loeb points out something else that makes this hypothesis compelling. If there is a fragment cloud, its combined surface area could be much larger than the main nucleus. Imagine 1 trillion tiny fragments. Together, they weigh just 1,000th of 3I Atlas's total mass. But because they are broken into so many small pieces, they would have 100 times more total surface area exposed to the Sun compared to a single solid object of the same mass. Surface area determines how much ice can sublimate when heated by the Sun. More surface area means more ice turning into gas all at once. More gas means brighter appearance, which means more visible tails and jets. This is a basic principle of thermodynamics. When you break a block of ice into tiny shards, the total surface area increases dramatically, even though the total mass stays the same. And more surface area means faster sublimation. This could explain several puzzles that have been bothering astronomers. It could explain why 3I Atlas appears so bright for its estimated size. If the brightness is coming not just from a 3-mile nucleus, but from trillions of tiny fragments with vastly more combined surface area, then the brightness makes more sense. It could explain why calculations suggest it is losing more mass than it should physically be able to if it were one solid intact object. If the mass loss is distributed across a swarm of fragments, then the total rate of sublimation can be much higher. And it could explain why the jets stay so straight and collimated instead of getting smeared out by rotation. If the jets are coming from many small fragments rather than from a single spinning nucleus, the collimation might be easier to maintain. This swarm hypothesis is just that, a hypothesis. It has not been confirmed. The November 11th images showed the nucleus still appears to be intact. Scientists specifically looked for signs of fragmentation using multiple image processing techniques and found nothing. They applied contrast stretching, subtracted background signals, and looked for any hint of multiple distinct objects near the nucleus, and the images did not reveal any clear signs of fragmentation. So if fragments exist, they would have to be very small, much smaller than the resolution limit of current telescopes. They would have to be so small that even when combined, they do not show up as distinct objects but only as a diffuse glow around the main nucleus. That is possible, but it means we do not have direct visual confirmation of the fragments. We only have the indirect evidence from the anti-tail structure and the brightness calculations. Now the second strange behaviour. Scientists have been tracking how 3I Atlas's brightness changes over time. The object gets brighter in a perfect rhythm every 16.16 hours like clockwork. This is not a rough approximation. The period has been measured with high precision across multiple observation cycles, and it holds steady at 1616 hours. At first, astronomers thought this was just the object spinning. Periodic brightness variations are often caused by rotation. If a comet has an irregular shape, or if one side is darker than the other, then as it spins we see the brightness rise and fall in sync with the rotation period. This is a well-understood phenomenon, but when they looked closer at the data, they realized the brightness changes are way too large to come from rotation alone. Less than 10% of the light we see is coming from the solid nucleus. More than 90% is coming from the coma, the cloud of gas and dust surrounding the nucleus. That means the brightness variations are not primarily driven by the shape or albedo of the nucleus itself. They are driven by changes in the coma. The coma is getting brighter and dimmer in a 16.16-hour cycle, and that requires an explanation that goes beyond simple rotation of an irregularly shaped nucleus. If gas is flowing out at 980 miles per hour, then during one 16-hour cycle, that material travels about 15 to 900 miles before the next cycle starts. This distance matches what observers are seeing in the images. The coma appears to be pumping up and down in brightness. You can see the coma expand as fresh material flows out, then fade as the material disperses, then expand again when the next burst arrives. The cycle repeats with remarkable regularity. Periodic brightness variations like this are not unprecedented. Comet Halley showed brightness variations with a 7 to 8 day period. Comet C 2013 A1 siding spring had an 8-hour cycle, and Comet 2P Encke showed an 11-hour period. So periodic pulsing from rotation is actually pretty common in comets. Astronomers have catalogued many examples over the decades. But here is what makes 3I Atlas different. In those comets, the brightness changes came from the shape of the spinning nucleus. Different parts of the surface have different brightness, so as it rotates, we see variations. But with 3I Atlas, the coma itself is actively pumping up and down with each rotation cycle. The amplitude of these variations is also unusually large, at tens of %, which suggests very strong periodic outgassing. In most comets, the brightness variations from rotation are a few % at most. With 3I Atlas, the variations are much more dramatic. That implies the outgassing is being turned on and off very strongly with each rotation, much more strongly than we typically see in comets from our own solar system. The most likely natural explanation is thermal cycling from an active ice region. 3I Atlas probably has a large pocket of ice on one side of the nucleus. As the object rotates, this ice pocket faces the sun once every 16 hours. Solar heat causes the ice to sublimate rapidly and shoot out a burst of gas. Then the pocket rotates away from the sun and the gas flow slows down. 16 hours later, the pocket faces the sun again and another burst shoots out. This creates the pattern where the coma gets filled with fresh gas and dust every rotation, then fades, then fills up again. This model is straightforward and relies on well-understood physics. Solar heating drives sublimation, and rotation modulates which part of the surface is exposed to the sun at any given time. Avi Loeb has pointed out there is a way to test if this natural explanation is correct. If solar heating is driving the pulses, then the bright jet must always point toward the sun when it pulses. That is the only direction where solar energy can heat the ice. You cannot have a jet pointing away from the sun that is driven by solar heating, because the sun is not illuminating that side. So if observers can measure the direction of the jet during each pulse and compare it to the sun's position, they can test whether the thermal cycling model is correct. Loeb also notes that if the jet points in directions that have nothing to do with the sun position, that would be harder to explain naturally. He has suggested that could indicate something else is creating the pulses, something that is not tied to solar heating. But right now, most scientists think the thermal cycling explanation fits the observations well. The period matches the expected rotation period, the amplitude matches what you would expect from strong periodic outgassing, and the overall behavior is consistent with known comet physics. Now, the chemical anomaly. Astronomers have been trying for months to figure out what 3I Atlas is actually made of and what chemicals are coming off of it. The data just came back from the ALMA radio telescope, which detects the exact molecules floating in space. ALMA works by observing the specific wavelengths of radio emission that different molecules produce. Each molecule has a unique spectral signature, so by measuring the radio emissions, you can identify which molecules are present and how much of each one there is. ALMA found two specific chemicals coming from 3I Atlas, methanol and hydrogen cyanide. Finding these two molecules in space is totally normal. Methanol and hydrogen cyanide are common chemicals in comets. We expect to find them. They form naturally in the cold environments where comets are born, and they are routinely detected in comets from our own solar system. But the ratio is what is weird. ALMA revealed that at first the ratio was 124 to 1. 3 days later it was 79 to 1, so the ratio is not only extreme, it is also changing over time. In normal comets, the methanol to hydrogen cyanide ratio sits around 10 to 1, maybe 20 to 1 at most. That is the baseline we see across hundreds of comets. Out of thousands of comets scientists have studied, only one has ever shown a ratio this extreme. A comet called C 2016 R2 Pan-STARRS had a ratio around 100 to 1, and scientists consider it a total freak of nature. They still have no idea why its chemistry was so weird. It does not fit any of the standard models of comet formation, and now 3I Atlas is showing a similar unusual ratio, except C 2016 R2 formed in our solar system. 3I Atlas formed in a completely different star system light years away. So we have two objects with freakish chemistry, and they both somehow ended up with nearly identical ratios despite forming in totally different parts of the galaxy under completely different conditions, from completely different clouds of gas and dust. That coincidence is hard to explain. But ALMA did not just measure how much of each chemical there is, it actually found where on the comet these molecules are coming from, and this is where everything gets really weird. Methanol is concentrated on the sunward hemisphere. The side of the comet facing the sun is blasting out methanol at way higher rates than the other side. But the hydrogen cyanide is doing the exact opposite. It is concentrated on the side pointing away from the sun. This is not a small difference. The concentration gradient is strong enough that ALMA could clearly distinguish the two hemispheres based on their chemical signatures. You can map where the methanol is coming from and where the hydrogen cyanide is coming from, and they are on opposite sides of the object. So we are not looking at a uniform ball of ice that is the same all the way through. This is an object where one half has completely different ice composition than the other half. It is like someone took two totally different comets and glued them together. One hemisphere is rich in methanol, the other is rich in hydrogen cyanide, and the boundary between them is surprisingly sharp. This is the first time scientists have observed an object from another star system in enough detail to see this kind of chemical separation. We have seen some solar system comets with active regions on different parts of the surface, but those are just pockets of ice that happen to face the sun at certain times during a comet's rotation. The active regions shift as the comet rotates, and the chemistry is generally uniform across the surface. 3I Atlas is different. This is an entire hemisphere showing one chemistry, and the opposite hemisphere showing completely different chemistry. The separation is large-scale and stable. There are two possible explanations for this chemical anomaly. The first hypothesis is that 3I Atlas formed in a region of its home solar system, where different types of ice were layering on top of each other. Maybe the protoplanetary disk around its parent star had chemical gradients so that ice forming in one region had a different composition than ice forming in another region. And maybe 3I Atlas incorporated material from two different regions as it formed. Then maybe one side has peeled off more layers as it has been travelling for billions of years. Cosmic rays, micrometeorite impacts, and gentle sublimation could have eroded one hemisphere more than the other, exposing deeper layers with different chemistry. But this explanation makes no sense, because comets are constantly spinning as they are flying through space. If 3I Atlas has been spinning every 16 hours for the billions of years it has been travelling through interstellar space, then any erosion should have been roughly symmetric. There is no reason why one hemisphere would erode much more than the other. The sun during interstellar travel is too distant to create a stronger symmetry, and cosmic rays come from all directions. The second possible explanation is that cosmic rays are the reason for this anomaly. Cosmic rays are high-energy particles, mostly protons, constantly flying through interstellar space. These particles can penetrate the surface of a comet and trigger chemical reactions. Maybe those particles hit one side more than the other and change the chemistry. If 3I Atlas was oriented in a particular way during its long journey through interstellar space, perhaps one hemisphere was exposed to a stronger flux of cosmic rays than the other. Over billions of years, this could in principle create a chemical gradient. But again, that would require the object to maintain the same orientation for an extremely long time, which is basically impossible because 3I Atlas makes a full spin every 16 hours. Even if there were some preferred orientation due to magnetic fields or tidal effects from nearby stars, the timescales involved make it implausible. The object has been tumbling through space for billions of years, and maintaining a fixed orientation for that long is not consistent with the dynamics we expect. As of right now, no scientist has come out and explained this anomaly. The methanol to hydrogen cyanide ratio and the hemispheric chemical separation remain unexplained by conventional comet models. Researchers are still analysing the ALMA data, looking for clues in the detailed spectral signatures and trying to develop new models that could account for what we are seeing. But so far, no consensus has emerged. And even though Avi Loeb has suggested technological hypotheses that remain unconfirmed and highly debated, he is actively trying to explore the anomalies of 3I Atlas in ways that push the community to reconsider standard models. The swarm hypothesis, the pulsing mechanism, and the hemispheric chemical split are all open questions. Each one challenges our understanding of how interstellar objects behave, and each one demands more observations, more data, and more rigorous testing before we can say with confidence what is actually happening with 3i Atlas.